Hello everyone, welcome to AWM Pitt Grad Seminar. Thank you for joining today. And today we have two speakers. First one is Maria Strazzullo, if I'm saying wrong. And she is a PhD student from SISSA, Trieste, Italy. And her topic is the role of optimal control of bifurcating phenomena and application to Navier-Stokes equation. And our second speaker, her name is Shihui Shei. She is a PhD student from University of Pittsburgh, and her topic is new ideas for penalty method. So please, Maria, you can go ahead.
Great. So I share my screen. I try at least. Okay. So you see my presentation?
Yes.
Great. And you see my pointer now?
Yes.
Great. So thank you very much for the invitation, and thank you for, this kind introduction. And yes, as I already told to Farjana, I am actually, I finished my PhD 2 months ago, and I work on optimal control and reduced order modeling for optimal control. But today I want to talk about a more specific topic, actually, that is the role of optimal control in nonlinear analysis and bifurcating phenomena. So this is actually, let's say, a chapter of my PhD thesis, but I wanted to present to you this topic because I think it's quite of interest and quite unusual, let's say. So this is a slide of outline. I don't want to spoil much, but I would like to take advantage of this slide to thank my collaborators. First of all, my colleague and friend, Dr. Federico Picchi. Federico Picchi now is a postdoc at EPFL, Lausanne, and he works with bifurcating phenomena. And then I would like to thank my advisors, so Dr. Francesco Ballarin and Professor Gianluigi Rozza. The work is basically this. You can find this paper online on arXiv, and there are the numerical results and the theory that I will try to present in 30 minutes today. And all the results have been coded with these two open source libraries that we developed at SISSA MATLAB, the research group where I work in, actually. And they basically deal with parameterized PDEs and coupled systems. So you can go, on Google, find it, it's open source, and you can play with the libraries and also with the tutorials. We have a lot of tutorials on Colab, so it's also quite easy to, follow that and play with that. So if you are interested. Now, let's go into the problem. So talking with Federico that works and introduced me to bifurcating phenomena, he told me something about the Coulomb effect. So the Coulomb effect is something that happens in every day, let's say, in our body, and it's a phenomenon that it's related to hemodynamics. So let's start our analysis from this echocardiography here. So in our heart, there is a mitral valve. This is an echocardiography representing the mitral valve, and the blood basically can flow in a straight way like that. So if the heart is pumping in a subtle way, it goes straight like that. But if it pumps strong enough, it can attach it to the floor, to the wall of the mitral valves. So this phenomenon can be actually modeled through Navier-Stokes equations. So steady Navier-Stokes equation, as you can see here, and by a parameter, okay, so a diffusivity parameter. So if the parameter is small, it means that basically the Reynolds number is higher, so the heart is pumping a lot, and something of this kind can happen, while if the parameter is high like that, basically the diffusivity is high, and you will have a Stokes type flux like that. So this phenomenon can be represented in this domain. This is a sudden expansion channel, so it's a representation of the mitral valve. You will have the flow going here in the channel, go out here on the right side of the channel, and then you have a homogeneous Dirichlet boundary condition on the walls. Great. But what happens if I simulate this problem for several parameters? Well, as we can see in this video, in this movie, basically after this value of the parameter and for smaller parameters, it happens that two configurations here arise and they coexist. So basically you have, I mean, the unicity is not longer guaranteed and your problem now has lost the unicity. So from this parameter on, you are able to simulate the two, okay, the two behaviors that you can have in your meter bulb. However, the Wall-Hugging phenomenon here, it's, let's say, bad from a medical doctor point of view. This because basically here you can have some circulation, some recirculation of your flow, of the blood flow, and this can be somehow an issue for measurements. So doctors actually do not like this configuration. However, this configuration is physically stable. What does it mean? So basically, in nature, you will always find this configuration. This means that for this geometry and parameters that are smaller than this one, you will always observe something like that and never something like that. However, mathematically, this is a configuration that can happen. Now, the problem is that in the real world, you have that and you don't like that. Great. In mathematics, you can give a, let's say, definition of physically stable, and is related to the eigenvalue analysis of your problem. So here there are what I call the bugs plot, because the bugs plots, because they look like bugs to me. But basically, this is a plot of the eigenvalues of a discretized system. So imagine that the previous equations that I showed you before are discretized, I don't know, like with a finite element method, we use finite element, and you plot for a chosen parameter, you know, the eigenvalues of that system, of the discretized system. What you have is that for the stable solution, the real part of the eigenvalue is always negative. Okay, so as you can see here, basically, you never touch zero. Actually, here in the close up, you can see that you never touch zero and everything is negative. And you see, this is the Wall-Hugging solution. So this is the physically stable one. While for the straight solution, that is the one that is unstable, you have that the real part of the eigenvalues of your discretized system crosses the zero. Okay, so this is a mathematical way to see if a solution is stable or unstable. Now, the question is, can I change this feature somehow and change the system in order to do not have bifurcations eventually and only have the straight solution here? And this is where optimal control, can be used. And we thought that maybe it could be a way to change the system and to reach, a stable behavior that is different from the Wall-Hugging one. So now, if you are not familiar with optimal control, I will try to give you an insight on it. So it is an input-output system. Basically, as an input, you have your PDE, a data, in our case, the parameter, and then you have a control variable. So the control variable is an external variable that acts on the PDE in order to change its behavior, minimizing a cost functional. I will be more detailed later, but now I want to only to give you, the flavor of that. So you minimize this cost functional, and in the end, you reach eventually an optimal solution that is similar to the data that you have. So now, basically, we want to use a data and an optimal control construction in order to reach the good behavior, so the straight one, okay? And we applied several control, and the questions that we wanted to answer were exactly that, like, can we change this behavior? Can we have the straight flux? And what about the physical stability of this straight flux? Great, so this is the problem formulation. Now, this is, let's say, a tough slide if you haven't seen this ever, if you have ever seen the optimal control. So I will read it with you. So given a parameter in a parametric space and a data taken in a subset of my domain, here I call this subset with omega ops, okay, and a forcing term, I want to find a state Y and a control U in some suitable Hilbert spaces, let's say, that minimize a functional subject to a PDE, a nonlinear PDE. So the functional actually it's of this form usually. So it is actually, it minimizes, let's say, optimal control minimizes the distance, okay, between the optimal solution and the data paying with respect to the control magnitude, okay, in L2 norm. Now, alpha is a penalization parameter. So basically, if alpha is small, you can control a lot your system because this norm does not weight on the functional, so the control variable can act as strong as it wants, okay? But if alpha is like higher, basically you cannot control much your system, right? Because this norm will weight on the functional, and it will be, let's say, smaller with respect to smaller value of alpha. Great. Now, the problem is constrained in the sense that there is a nonlinear controlled equation that depends on a equation, let's say, on a contribution of the state and a linear contribution of the control, and you see the forcing term. Now, the contribution of the state is basically divided in a nonlinear part, okay, and a linear part. It's a classical Navier-Stokes equation, for example. The control here can act actually on the whole domain, on a portion of the domain, or even on the boundary. So we tried several control, and we will say that the control acts on omega u, that is actually a subdomain of the domain or even a boundary portion. Now, how can I solve this problem? Well, I can use Lagrangian formulation. So it's a classical approach. Basically, you define an adjoint variable in the state space. You build this global space, okay? And your global solution now it's a triplet. So given by the state, the control, and the adjoint. You build the Lagrangian functional given by your previous functional plus the weak formulation of your constraint tested with respect to your adjoint. And it can be proved that basically the minimum of this problem here is actually a stationary point of the Lagrangian. So what you do, it's like you differentiate with respect to the state, the control, and the adjoint. You put everything equal to 0. You find this triplet here, and it's the optimal triplet, and Y and U represent the control pair, the optimal pair of the minimization problem. Now I will call in this way, you know, the strong form of the optimality system. Now the problem is that the uniqueness of the solution of this problem is related to the uniqueness of the solution of the state equation. So somehow the optimal control problem inherits the loss of the uniqueness, okay? So the problem of the invertibility of the state equation. Our goal was to like build a discrete framework that was able to understand, you know, how the control variable at least changes the behavior of this, of the multiple solutions, okay, and their stability. How can we do that? So as I told you, we used finite element, the finite element method, and actually we needed an algorithm that was able to do basically two things. First of all, you have to detect the bifurcation in the sense that if you simulate for several parameters, you have to be able to build a bifurcation diagram like that. So this is a classical representation of the pitchfork bifurcation arising in the sudden expansion channel. So what you have is that you are printing a quantity of interest. Here we have, for example, the vertical velocity in a point. And you see that for high diffusivity, you have only one solution. but then something bad happens around 0.96, as I told you before, and 3 solutions coexist. 2 that are physically stable, the upper branch and the lower branch here, and the one that is unstable. Great. So you need to detect the point and also understand the stability of the solutions. As I told you, stability is related to eigenvalue analysis. So now in the optimal control setting, actually, you can perform 2 eigenvalues analysis, because you have the state equation eigenvalue analysis. This is the state equation. And also in this case, if you have negative eigenvalue, it means stable solution, and positive eigenvalue, unstable solution. But then you have also a global optimality system that can be linearized, and you can study the eigenvalues of that. But what does it mean? I mean, there is no literature about that. And now I will try to let you understand what are the characteristics and the features that you can recover from this problem here. This is the algorithm that we use, is a branch reconstruction algorithm based on continuation method. So the idea is quite easy. So you start with an initial guess, okay? And for each parameter, what you do is that you solve the Newton's method, but with guess the previous value, the previous solution with respect to the parameter space. So you solve the optimality system, as I've written here, with the guess as the solution related to the previous move, okay? So you're somehow helping the solution to follow the branch, as you can see here. Great. And once you solved this, for each parameter, you study the eigenvalues. In this way, you are basically able to follow a branch, okay, and to study the stability. In order to find the other branches, there are, several techniques, but basically you can act on the first step, so on the first initial guess. If you act on that, you are able to choose which branch to follow. Now, I don't want to be really detailed, but basically this is an important step in order to find all the 3 branches. Great. Let's start with some numerical results. We put together a very simple optimal control, but still the results were quite interesting. So the problem that we want now to solve is the following. Given the usual parameter in the usual parametric space, I want to find the triplet given by the velocity, the pressure, and the control, okay, in these Hilbert spaces that minimizes this functional constraint to Navier-Stokes equation, but in this case, they are controlled, okay? So here, this operator can represent, a control all over the domain or on a boundary. I mean, it's a general formulation up to now. Yes, and the functional is given by the L2 norm over gamma ops of V minus VD. Now, gamma ops is this line here, so it's a line at the end of the channel, and VD is a symmetric Stokes flux. So basically, we want our system to be as diffusive as possible, okay? So we have that, and as you can see, as usual, we have the L2 norm of the control, okay, penalized by alpha. Great. Now, we tried a lot of control. Actually, in the paper, we have like 4 types of controls, but here I will show you, I mean, for the sake of brevity, only 2 of them. But what I want to let you understand is that basically the problem is very complicated. There are a lot of, features. There is the parameters, there is the penalization parameters, there are several controls. So you can have a very weak control, okay, on the outflow boundary, for example, but a very strong control all over the domain that is able to straighten the flux quite easily. Or you can change alpha and you can have very different stability issues if you change alpha, and so on and so forth. But I will show you only let's say, the worst case scenario, so the weaker control, on the outflow boundary, and the boundary flux control, okay, that changes completely the behavior of the stability of the solution and of the system. So, and for the test cases that I will show you, we will analyze together the solutions, the action of the control, and the two eigenvalues problem. So let's start with the worst case scenario. So the first optimal control that we put together is actually really classical, at least in the, hemodynamic field and the numerical analysis related to hemodynamics. So basically here, you are controlling the Neumann condition. So actually you are trying to change how the flux exits in order to achieve a Stokes flux here on the light blue dashed line. Okay, so you have your inlet condition, it goes, let's say, straight, or you have a wall-hugging solution, and you try to straighten it somehow and to make it more diffusive. What happens here, sorry for the typo, what happens here is basically that you have two solutions here. Okay, so actually it's not very different from classical Navier-Stokes. You have only a mild diffusive effect over the observation domain. Indeed, for alpha equal to this value and mu equal to this value, what you have is that you can find two coexisting solutions. So the straight one and the wall-hugging one, okay? However, we are controlling the system, as I told you, because if you plot the velocity magnitude in line here, over this line here, we see that we are controlling the system. Since if you follow the blue line, you have the desired Stokes profile. The green line here is actually the standard Navier-Stokes without control, so it's really asymmetric. While the controlled system gives the orange line. So you see that I'm recovering somehow the symmetry, but okay, the magnitude is higher for sure. How the control acts? Well, here you have a plot of the control, so of the value of the control here for several parameters. And when the parameter is high, so for mu equal to 2, for example, basically there is no control, while when we are somehow approaching to the bifurcation parameter, that is 0.96, you see that basically the control tries to really modify somehow the asymmetric profile here, and is trying somehow to make it straight. And it's really, asymmetric, as you can see. This is the spectral analysis, like the global one. And it's very different from the box plot that you have seen before. This is because in the optimal control, you have the matrix is symmetric. In the optimal control governed by Navier-Stokes equation, the matrix is symmetric. And so all the eigenvalues are real. So here we are plotting the real part of the eigenvalues of the system, okay, with respect to several parameters. And what we can observe is that there is this strange phenomenon that we call the shears phenomenon, because you have the eigenvalues, two eigenvalues, one positive and one negative, that are approaching to 0, but they never touch 0. We do not have close-ups, but they never touch 0. But let's say the nearest point to 0 is actually where the bifurcation is happening. So global eigenvalue analysis gives you an information on where the bifurcation is happening with respect to the parameter, okay? And there is another information that is given by the cluster of positive eigenvalues, because if the system is really, let's say, controlled, so if alpha, as you can see, is smaller, you have a lot of positive eigenvalue with respect to the negative one, okay? So if in these plots you have a lot of positive eigenvalues, it means that you are controlling a lot your system. And if you have two eigenvalues approaching, one from the top and one from the bottom to 0, it means that something very strange is happening, like a bifurcation phenomena in the pitchfork bifurcation framework. I'm not showing you the bugs plot, so the ones that I showed you, the colorful ones that I showed you before, because they are very similar to Navier-Stokes one, the standard. So for the wall-hugging solution, you have all negative eigenvalues, real part eigenvalues, and for the straight solution, you have the crossing of the origin. Now the best case scenario. So this is the Dirichlet control. Basically here, the control allows the flux to do whatever it wants in these two portions of the boundary. So it can go out and it can be injected, okay? Now we wanted always the Stokes flux here at the end of the channel. And what happens here is that we can find only one branch for each parameter. Now you see two plots here, but actually they are related to two different models. Indeed, for alpha equal to 1 and for mu equal to 0.5, we were able to find only this straight solution here. Okay, really diffusive here. While for very small alpha, we were able to find this really diffusive solution. As you can see here is basically Stokes, but with a very, strange behavior, okay? And what is happening? As I told you, the solution basically is Stokes. As you can see here, the Stokes velocity and the controlled velocity for a small alpha is basically the same. So you are controlling a lattice system, okay? But what you are paying is that in order to achieve this very diffusive effect, the control injects a lot of asymmetric flows, okay? So as you can see from the peaks here, okay, this is a plot of the control with respect to alpha. So you have the peaks here, and it means that you are injecting flow, and it causes something very strange here. While here, it happens that the control only let the flow to go back, so somehow to go out from the mitral valve, to avoid, circulation here and to make the flux straight. Now, plots of the eigenvalue. This is the global spectral analysis, as I told you. So the one with only real part, because it's the one of the linearization of the optimal control system, okay? And as you can see, the eigenvalues are all positive. So here we are actually thinking that in the parametric space that we are looking into, we got rid somehow of the bifurcation, okay? Because the shears are not happening in this sense. However, for the very small alpha, something very strange is happening. It's the first time that we see the eigenvalue crossing the origin, okay? So I will give a hint of that in the next slide, but from the eigenvalue analysis here, we can understand that something very strange is happening, not related to the pitchfork bifurcation that we were studying and investigating. Now I'm plotting also the box plot for you. Okay, I'm showing you the box plot. So on the top, you have standard Navier-Stokes with no control. So let's recap. If you have the wall-hugging solution, the real part of the eigenvalues of the discrete system are all negative, great. If you have the straight one, basically the real part crosses the origin. Okay, now what happens in the Dirichlet case? Look at this. So you have the straight one, but if you look at the eigenvalues, they are all negative. So actually, the solution that we found with the alpha equal to 1 gives you a straight solution and a stable straight solution. So we reached somehow our goal. While the one that is very diffusive, but it's very strange at the beginning of the channel, so have a very strange behavior. You see some eigenvalues crossing the origin, but also some, let's say, the imaginary part also crosses. So basically here we are in another framework, the off bifurcation. So a deeper analysis. We have to make a deeper analysis on that, but it's very interesting. Now, how can we study all that, because there are a lot of parameters. Actually, I have a very small time, as I can see from my, from my phone, but basically we used reduced order modeling, and reduced order modeling is a way to exploit the parametric structure of your problem in order to solve your problem for several parametric instances in a faster way. Now, I will go fast to that. So reduced order modeling, it's like an approximation of the approximation. So imagine that you have your continuous solution, you apply, let's say, a finite element approximation, you assume that is quite a good approximation. You apply an algorithm to build a low dimensional framework that is a subset of your finite element, and you project everything on that finite element, on that reduced order mode, okay, in order to have a faster solution that is, let's say, a good representation of your finite element solution. How can you do that? We use proper orthogonal decomposition. I don't want to be detailed in that, but it's a observe and compress algorithm, in the sense that you look at the solution and how it varies with respect to the parameter. You build a covariance matrix for a lot of snapshots. Okay, so you pick a lot of finite element solution, you build the covariance matrix, and you retain the n eigenvectors related to the n largest eigenvalues, and they basically are a very informative basis of the behavior of your solution, changing with respect to the parameter. The important thing is that basically capital N is much lower than calligraphic N, and so you gain a lot of computational time to solve the problem for several parameters. So a last slide of results. Here we plot basically how the relative errors, average relative errors of over a space of a parametric test set with respect to N. And you see that for the Neumann control, it goes everything quite well. For the Dirichlet control, we had some troubles, but state and control and state pressure and state velocity and control were quite well approximated. But the most interesting plots are this one, because here we fix, the N, let's say, to 20, and then we plot the relative errors with respect to the parameter. So it's like, a mood-dependent error. And you see some peaks here. And basically the peak gives you an idea where something bad is happening. So reduced order modeling can help you in order to understand where the bifurcation is happening, okay? And for the Dirichlet problem, basically, we totally lost the standard bifurcation point for 0.696, but we have a very strange behavior, as I told you at the beginning of the interval. So that's it. I'm a bit over time. So I thank you for your attention. And if you have questions, I'm here to answer you. Thank you.
Thank you, Maria, for the talk. I'll go ahead and stop recording for now.